Sacrificial layer etching. Know that sacrificial layer etching is a critical step in surface micromachining. Let's first take a look at PSG, sacrificial etching in microchannels. I pretty know that PSG stands for phosphosilicate glass. It's simply silicon dioxide doped with phosphorus pentoxide. And we typically use 6% P2O5. We have just studied PSG in chapter 6. This is PSG is a popular sacrificial material because it has a much faster etching rate than low temperature oxide. To study PSG sacrificial etching, PSG is as shown in this figure. PSG is encapsulated inside silicon nitride channels. So the channel, this channel wall is made of silicon nitride. We know that this is a low stress silicon-rich silicon nitride, because the stoichiometric silicon nitride has a very large stress. So, and we typically do not use stoichiometric silicon nitride. Then the channel is opened at one end. For example, in this case, it's a left end. Then we immerse the chip in HF solution. So PSG is etched by HF. Then under the microscope, this is the picture taken under the microscope. So under the microscope, we can measure the etching length as a function of time. We know that microchannels are opened on the left end. On this figure, we can see that you can see this is the etching from. So this distance is the etching length. Or from this cross-sectional view, this distance is the etching length. So we can measure the etching length as a function of time. This figure plots the measured etching length as a function of etching time for HF from 3 to 49%, a different HF concentration. We can observe that the higher the HF concentration, the faster the etching. This curve stands for 3.6%, 3.6. And this one stands for 49%. So the higher the HF concentration, the faster the etching. This is kind of obvious. In addition, we can observe that the etching rate is not a linear function of time, or it's a non-linear function of time. Know that the etching rate, this etching rate is equal to the slope of these curves. Namely, it's equal to dL over dt. L is the etching length, T is the time. So that's simply the slope of the curve. So we can observe that this etching rate is not a linear function of time. Or we can state that the etching rate, the etching rate decreases when the etching length L increases. So the etching rate decreases over the etching length or over the etching time. Then we can conclude that this etching is a mass transport limited process. Okay, so this is a conclusion. We conclude that this etching is a mass transport limited process because HF need to be, okay, let's go back to the previous slide. Right, HF, okay, this is the etching. HF need to be transported from the opening of the channel to the etching front. Right, this is a mass transportation. And it's kind of obvious that the longer the etching length, the more difficult to transport HF, or it takes longer time to transport HF. Right, so that's why the etching rate decreases over time. Make sense? Know that the etching rate is a function, or is determined by two processes. First is this mass transport. Mass transport process. Second is a surface reaction, surface chemical reaction. Okay, right. These two processes occur in series. Right. First, HF need to be transported to the etching front, right? Mass transportation. Then second, HF need to react with PSG at the surface. Okay, so these two processes occur in series, and the etching rate is determined by the slower process. Right. In this case, mass transportation is slower, so it's the etching rate is determined by the mass transport, and the etching rate decreases over time. If the etching rate is determined by surface reaction, what kind of etching length versus time curve do you expect? By assuming let's assume the temperature is constant. Then we will observe linear curves. Okay, if it's determined is dominated by surface reaction, then we will expect linear curves. Polysilicon sacrificial layer. Note that polysilicon is typically used as a structural layer, but it can also serve as a sacrificial layer, can be used as a sacrificial layer as well. When polysilicon is used as a sacrificial layer, the structural layer is typically silicon nitride. Again, it's a low stress, silicon-rich silicon nitride. And the etchant is a KOH or TMAH. Right, KOH and the TMAH are anisotropic silicon etchant. Right, we can use them to etch polysilicon as well. To study polysilicon sacrificial etching in TMH, long strips of polysilicon were encapsulated inside the silicon nitride channels. Again, we use silicon nitride channels, microchannels. Then the channels were opened at one end. Now it's opened on the right end. Okay, right end of the channel are open. And the chip was immersed in TMAH solution. Okay, so the polysilicon will be etched by TMAH, okay, starting from this opening. This figure plots the etch length, the etching length, okay, this distance, as a function of time. And it's very interesting that now we observe linear etching length versus time curves. We observe linear curves, which means the etching rate is constant. Okay, the etching rate remains constant over time or over the etching length. Then we can conclude that for polysilicon TMH etching, okay, inside microchannel, mass transport does not limit the etching rate. But why it's linear? Well, this is what we observe, right? It's a linear curve. Okay. But why these curves are linear? Why are these curves linear?
Surface reaction.
Surface reaction, okay. But that's what we observe. Okay. But why? Okay. In the previous case, we can see it's mass transport limited, right? Because the etching needs to be transported from the opening to the etching front, and the longer the length, the more difficult the transportation, okay, or the slower the transportation. So the etching rate decreases. So very easy to understand. But why do we observe these linear curves? I will assign this as a actual credit problem in homework. Okay, so you can work on this problem. Then you can do some probably little search or Google search, okay, or just use your own imagination to give a plausible explanation. Know that it does not need to be very rigorous, as long as you can provide some explanation or hypothesis to explain this phenomenon. Boron etch stop in polysilicon. Previously, we studied the boron etch stop in single crystal silicon. Now we can see that polysilicon has also boron etch stop feature, which can be used to control the sacrificial etching. The left figure plots the relative etch rate of polysilicon versus the boron concentration for TMAH at 90 degrees C. And we can observe that the etching rate can be reduced by 10 to 100 times by heavily doping polysilicon with boron. The horizontal axis is boron concentration. Similarly, in the right figure, which represents the relative etch rate versus the boron concentration for QH at 80 degrees C. Okay, so in this figure, again, we observe that the etching rate can be reduced by 10 to 100 times due to the boron etch stop. As shown in the bottom figure, right, the heavily doped polysilicon can function as a etch stop. It can be used to control the sacrificial etching. So this is actually a useful feature in sacrificial etching. Gas phase etching using bromine trifluoride and Zener difluoride. Again, previously we have introduced bromine trifluoride and Zener difluoride etching for single crystal silicon. And know that polysilicon can also be etched by bromine trifluoride or Zener difluoride. Actually, all silicon etchings we learned before can be used to etch polysilicon. This etching, right, bromine trifluoride or Zener difluoride etching is a room temperature process. Dry etching, right, no liquid. It's a spontaneous reaction or etching. It does not need plasma. No charging, right, no damage caused by charging. And this etching is isotropic, right? That's very important. So it leads to large undercut. Right? That's the reason we use this etching to etch polysilicon, right? To etch sacrificial polysilicon layer. No meniscus force, right? Since it's dry etching, so there will be no meniscus force. Again, microchannels were fabricated to study polysilicon sacrificial etching by bromine trifluoride. Polysilicon is encapsulated by silicon nitride or perylene. Know that perylene is a polymer material. Right? Later we will have a more detailed discussion. This figure plots, this figure shows polysilicon etching in silicon nitride channels under the microscope. Okay, it's a micrograph taken under the microscope. There are four silicon nitride channels which are opened on the left end. And this figure shows polysilicon etching inside a circular silicon nitride chamber. The opening is at the center of the chamber. And the bottom figure shows a square-shaped polysilicon film encapsulated by silicon nitride or perylene thin film. Then it is etched by bromine trifluoride from 8, right, 1, 2, 3, 4, 5, 6, 7, 8 etching channels. So bromine trifluoride can enter the chamber through these etching channels, right? Inlet. Okay. And we can observe that the etching fronts of polysilicon are circular. Okay. We observe the circular etching front. Right, this is a natural result of the isotropic nature of bromine trifluoride etching. Right? Bromine trifluoride etching is a isotropic. That's the reason we will observe these circular etching front. And the dark area is a remaining polysilicon. So it's not completely etched yet. This figure plots the etching depth of polysilicon inside silicon nitride channel as a function of number of cycles, number of etching cycles. Okay. And this horizontal axis is actually equivalent to etching time. So again, we observe these non-linear curves. So what's our conclusion? We can conclude that this bromine trifluoride etching is a diffusion limited or mass transport limited, right? Diffusion or mass transport limited. Polymer sacrificial layer. We can use a polymer as a sacrificial layer in surface micromachining. For example, photoresist or polyimide. The thickness of polymer sacrificial layer can be up to 100 micron. This is a big advantage compared to PSG or polysilicon sacrificial layer, whose thickness is typically 2 micron maximum. And the maximum thickness is typically limited to 2 micron. But if we use a polymer, this sacrificial layer can be as thick as 100 micron. Etching methods. PR, photoresist, can be etched by acetone, PR stripper, or oxygen plasma. The first two methods are wet methods. The third one, the last one, is a dry method. Oxygen plasma etching is a dry etching. Polyimide is typically etched using oxygen plasma. Issues of polymer sacrificial layer. Selection of structural layer. When polymer is selected as a sacrificial layer, the deposition temperature of the structural layer will be limited. For example, we cannot use polysilicon or silicon nitride as a structural layer, because their deposition temperatures are too high. The polymer layer will be damaged. So we have to select structural layers that can be deposited at a low temperature. Second, small etch rate for hardened PR and polyimide. Hardened PR and polyimide typically etched by oxygen plasma, which is relatively slow. So it may take a very long time to finish the sacrificial etching. The selectivity over other materials. Now let's take a look at an example which uses polyimide sacrificial layer. This SEM image shows an aluminum actuator or mirror. So this structure is a mirror, aluminum mirror, released by arc stream plasma etching of polymer. We know that this mirror or actuator is freestanding. It's released by arc stream plasma etching of polymer. So there be a polymer underneath, and which is removed by arc stream plasma. Let's take a look at the specific fabrication process. Right. After fabricating aluminum electrode and other structures on the substrate, a polyimide layer. Know that this layer, this thick layer, stands for the polyimide layer. Okay, so a polyimide layer is spin coated and patterned. Know that in this step, this post hole is patterned in polyimide layer. Okay, this post hole. Next, deposit and pattern an aluminum layer. Okay, so aluminum layer is deposited and patterned. Know that this aluminum is deposited inside the post hole, okay, to form the post structures. Right? As we can observe in this SEM image, this mirror, okay, this freestanding mirror, is supported by these two aluminum posts. Okay, aluminum posts. So in this step, what method should we choose to deposit this aluminum layer? Well, we have learned two methods: evaporation and sputtering. Thermal evaporation and sputtering. Which method is better to deposit aluminum in this step? Which method? It should be sputtering, right? Because sputtering provides better step coverage. Right? That's what we learned in chapter 5 or chapter 6. Okay, in the previous two chapters, right, we studied evaporation and the sputtering. Evaporation is a line of sight deposition, so it has a poor step coverage. And the sputtering, because of its much shorter mean free path, it has a better step coverage. So here it's better to use sputtering because we want to cover this post hole. We want aluminum to be deposited along this almost vertical side wall. Finally, this aluminum plate, aluminum mirror, is released by removing polyimide. Okay, the polyimide underneath is removed by oxygen plasma joint etching. And know that this mirror can be actuated by applying voltage between the plate and the bottom substrate. So we can apply a voltage in between. this voltage can actuate this micromirror, right, to tilt this micromirror. So the force is driven by this mirror is driven by electrostatic force. So in this example, polyimide is the sacrificial layer and aluminum is a structural layer. Another example. This example is actually opposite. We use aluminum as a sacrificial layer and polyimide as a structural layer. So it's opposite. And this example is a floating element shear stress sensor. So this is a sensor. So this is a sensor that measures shear stress. What is shear stress? This is simply a stress that is parallel to the surface. Or if this stress is perpendicular, we call this normal stress. If it's parallel to a surface, it's a shear stress. Right, for this floating element shear stress sensor, 3 micron thick aluminum layer is used as a sacrificial layer. Okay, so this layer, this aluminum layer is a sacrificial layer, right? 3 micron thick. And the polyimide is the structural layer. Okay, so the floating element is made from polyimide. Then this aluminum layer is removed by aluminum etching. This is a phosphoric acid plus acetic acid plus nitric acid. This is actually aluminum etching. It takes 2 hours to release 500 micron by 500 micron plate. After sacrificial layer etching, this floating element is free, is freestanding, or is floating. Right? Then if we apply a shear stress, this element will move laterally. Right, to move laterally. Right, this movement is caused by this shear stress. And know that an electrode is embedded inside this floating element. So the movement can be measured by measuring the capacitance between this electrode and the bottom electrode. Okay, so this is actually capacitive sensing. Capacitance is equal to epsilon A over D. Right. In this case, epsilon constant, D, the distance between the two electrodes, is almost constant. A is the overlapping area between the top electrode and bottom electrode. Now, when this floating element moves laterally in response to the shear stress, this overlapping area A changes. Then this capacitance changes. So we can measure the displacement, the movement, by measuring the capacitance. And this is the operating principle of this floating element shear stress sensor. Surface micromachining examples. Next, I'm going to introduce more surface micromachining examples. The first one is a resonant gate transistor, RGT. This device was developed in 1965, a long time ago. So this is one of the earliest surface micromachine devices. We actually already introduced this device in chapter 1, introduction. Simply speaking, the resonant gate transistor is a field effect transistor with a moving gate over its channel. We have source and drain, and this freestanding cantilever serves as the gate, serves as a moving gate. I can draw a cross-section view. Okay, let's draw along this cross-section. We have source, we have drain, and a freestanding gate. Okay. Note that this gate is not attached to the substrate. Okay. For a traditional field effect transistor MOSFET, we have an oxide layer, right, between gate and substrate, or between gate and channel. Now, this gate is freestanding. The input signal, we can apply input signal, and this input signal can move the gate up and down, vibrate the gate, modulating the channel resistance. So now the channel underneath, the channel connect source and drain, is modulated by this mechanical vibration. Right. The output signal is modulated by the mechanical vibration of the freestanding gate. Right. The idea is to take advantage of the high quality factor of mechanical resonator. Right. This Q stands for quality factor. Know that mechanical resonator has a much larger quality factor than that of electrical resonator. For a typical AOC resonator, inductor and capacitor, its quality factor is much less than 10. Okay, it's in single digits. On the other hand, a mechanical resonator has a Q value of thousands or even tens of thousands. A very high quality factor. Polysilicon surface micromachining. In 1980s, polysilicon surface micromachining was developed. This figure, the left figure, shows released polysilicon cantilever beam fabricated using a one-mask process. The polysilicon is a structural layer, and the PSG is a sacrificial layer, which has already been removed in this figure. The right figure shows a released doubly supported polysilicon beam. We call this a bridge, polysilicon bridge, fabricated in the same process on the same wafer. Okay, using the same process. Polysilicon is the structural layer, and the PSG is a sacrificial layer. Some polysilicon mechanical structures can be fabricated using surface micromachining, namely by consecutive deposition patterning of polysilicon structural layers and PSG sacrificial layers. This is a polysilicon surface micromachining. This SEM image shows a PinJoint. This shaft or shank can rotate around this central cap, which is anchored to the substrate. Okay, so this PinJoint can allows rotation. Okay, allow this shaft to rotate around the central cap. To better understand the structure of PinJoint, let's take a look at its fabrication process. So let's move to the next slide. The fabrication process of PinJoint. This is the top side view of PinJoint. This is the shaft. This is the central cap, and this is a cross-sectional view. So first, we can deposit the first PSG layer, and first polysilicon layer. Then pattern this polysilicon layer and the PSG layer. So that's the first step. Then deposit and pattern the second PSG layer. The second PSG layer is deposited and patterned in the step. Where is it patterned? Right here. And this will serve as an anchor hole for the central cap. It become very clear in step 3. Okay, in step 3, the second polysilicon layer is deposited and patterned, forming the central cap. Right, so the central cap is formed by second polysilicon layer, by poly 2. And we can say this cap anchors to the substrate due to the etching in step 2. Okay, this is the anchor hole. Okay, and the shaft which can rotate is made of first polysilicon layer. Okay. Right, this is this shaft, right? It's the first polysilicon layer, and the cap is the second polysilicon layer. And after sacrificial etching, this shaft becomes freestanding. Okay, but it's constrained by the central cap in the vertical direction and the lateral direction. So this shaft can only rotate. Okay, it can only rotate, but not translational movement. It can only rotate. The second image shows joint levers. And in this joint lever, there are two types of joints. These two are pin joints or fixed joint. We just discussed in figure 1. The second type is a self-constraining joints or free joints. Okay, these two are self-constraining joints or free joints. Free joints allow both rotational and translational movements. Okay, we can see why these two joints move away from the original position. We can tell from the marks on the substrate. Okay. Fixed joint or pin joints only allow rotation, no translational movement. But free joints allow both. Why can free joints allow both rotational and translational movements? To answer this question, let's take a look at the fabrication process of free joints. Deposit first PSG layer, then deposit and pattern first polysilicon layer. That's the first step. Then etch first PSG layer. Okay, the first PSG layer is etched using the first polysilicon as a mask, actually. Then deposit second PSG layer. Okay, so the second PSG layer is deposited. But know that for free joint, we do not pattern the second PSG layer. You can compare this step with this step for pin joint. You can clearly see the difference. Okay. Then deposit and pattern the second polysilicon layer. This is the second polysilicon layer. So this will form the cap structure. But this cap is not anchored to the substrate. You can see it's not anchored to the substrate. So after sacrificial etching, the shaft, again, the shaft is a first polysilicon layer, can have both rotational and translational movement. That is because the second polysilicon layer is not anchored to a substrate, so it allows both rotational and translational movement after sacrificial etching. But for pin joint, we can see the cap, poly 2, right? Second polysilicon layer is anchored to a substrate, so it only allows rotational movement. Questions? So in this slide, we can clearly see the relationship and the difference between pin joint and the free joint. They can be fabricated simultaneously on the same wafer with the same surface micromachining processes, except that for free joint, the second PSG layer is not patterned for anchor hole. Okay, so there's no anchor hole for free joint. But pin joint has an anchor hole. So that's the difference. Okay, now let's take a look at this SEM image. This SEM image shows a spring the pin joint. We can see a spring, a mechanical spring, connect the shaft and the cap. Okay, the shaft is connected to the central cap by a mechanical spring. The shaft can rotate by applying an external force. For example, we apply force in this direction, and then this shaft can rotate. When the external force is removed, The shaft can return to its original position due to the mechanical spring. This mechanical spring can have to restore the original position of the shaft. This figure shows a combined mechanism or slider structure. The shuttle can slide along the horizontal direction, along this direction, due to the constraint of this structure. So it can only slide along this direction. Then its teeth can push these two springed pin joints. There are two springed pin joints here. When released, this shuttle will be pushed back by these two springed pin joints. Questions? Another example. This this figure shows a pair of polysilicon tongs opened by pushing this handle forward. Okay, the handle is based on this slider structure, and the two arms of the tongs are constrained by two fixed joints or pin joints. The handle can only move linearly due to the slider. Then the fixed joints or pin joints convert the linear movement of the handle to rotation. Okay. So again, we know that the pin joints allow rotation, but not translational movement. Polysilicon micromolders. A polysilicon micromolder is probably the most famous surface micromachining example. As shown in this SEM image. This polysilicon micromolder consists of 3 parts: central cap, rotor, and stators. Note that the central cap rotor configuration is very similar to the pin joint structure. In some sense, this is simply a pin joint. This rotor can rotate around the central cap. The central cap is anchored to the substrate, so it only allows rotation. And this rotor can be driven to rotate by applying voltage to stators in sequence. For example, if we apply voltage to this stator, okay, and this stator, then this rotor will move counterclockwise, right? For example, a positive voltage here and a negative voltage here. Okay. So this rotor will rotate in this counterclockwise direction. Let's let's watch the video. Watch the video in chapter 1 again. Are you able to see the video screen?
Yes.
Yes. Great. Okay, excellent. So let's watch this video again. You see, this is the rotor, these are stator, and this is the central cap. Okay, so this rotation is driven by applying voltage to the stator in sequence. Any question? So which now you have a better idea of the operating principle of micromotor, of polysilicon micromotor. Okay, let's go back to our PowerPoint slide. Process a polysilicon micromotor based on MUMPs. Here, MUMPs stands for multi-user MEMS processes. It's a foundry service to make advanced MEMS technology available to all domestic participants at a very low cost and low effort. So it's analogous to MOSFET for CMOS fabrication. Some of you may have used MOSFET previously. Know that a lot of researchers do not have their own microfabrication facility because those facilities are very expensive. MUMPs enables those researchers to fabricate MEMS with a low cost, with a reasonable cost. The MEMS process has 3 polysilicon layers, 2 sacrificial PSG layers. It uses 2 micron rule, namely the minimum feature size is 2 micron. You will receive 15 pieces, 1 centimeter by 1 centimeter dies. So you will get dies instead of wafers. The cost is about $4,200. This is an academic rate. So a little bit over $4,000. Next, let's discuss the MEMS process of fabricating polysilicon micromotor. First, deposit 0.6 micron silicon nitride layer, then poly 0, 0.5 micron. Please note that poly 0 is actually the first polysilicon layer. As we just learned, there are 3 polysilicon layers. This poly 0 is the first polysilicon layer, which is a 0.5 micron thick. Then spin coat photoresist layer. Pattern this photoresist using photolithography. Then etch poly 0, first polysilicon layer, using this photoresist as a mask. Okay, so the pattern is transferred from the photoresist to poly 0. We call this a poly 0 etch. Then deposit and etch first oxide layer, or first PSG layer. Note that here is oxide stands for PSG, phosphosilicate glass. This yellow layer represents the first oxide layer, which is a 2 micron thick. And it's etched twice in this step. The first etch is a partial etch. This is a partial etch which etches 0.75 micron deep dimples. So we etch 0.7 micron deep dimples on this first oxide layer. Right? This oxide layer itself is 2 micron. So this is a partial etch. The second etch is this anchor 1 etch. Anchor 1 etch. Right? It's a complete etch. The pH layer is completely etched down to the nitride layer. So 2 etches, one is a partial etch, one is a complete etch. Later we will know the purpose of fabricating these dimples. Then deposit poly 1. We know that poly 1 is the second polysilicon layer, like 2 micron thick. This red layer represents poly 1. After poly 1 is deposited, a PSG layer is also deposited. So actually 2 layers, 2 thin film layers are deposited in the step. Poly 1 and PSG layer. Then the wafer is annealed at 1050 Celsius for 1 hour to dope poly 1 and reduce stress. So during the high temperature annealing, phosphorus in PSG will diffuse into poly 1. So poly 1 will be doped by phosphorus. Next, pattern poly 1. This polysilicon layer is patterned. Then deposit second oxide layer, or second PSG layer, 0.75 micron thick. Right, this is the second PSG layer, this green layer. And then etch second oxide layer. The second oxide layer is patterned. We call this P1, P2 via etch. Okay, so these areas are actually stator areas. We will fabricate stator here. Then etch first and the second oxide layer. This green layer and yellow layer are etched. We call this anchor 2 etch. This etch provides an opening for poly 2 to contact the substrate. Right, it's very clear in the next step. Right, in the next step, we deposit poly 2. The third polysilicon layer, which is 1.5 micron. Now we can see that this poly 2 layer anchors to the substrate. Right? It contact the substrate directly due to this opening etched in this step. Right? So it anchors to the substrate. Note that above poly 2, a PSG layer is coated. Okay, we call that PSG layer. And high temperature annealing is carried out to reduce stress and to dope poly 2. So poly 2 is also doped by phosphorus. Then pattern poly 2 layer. So this layer is patterned, is etched. And the central cap is formed here. Right, this is the central cap. And these are stators. Okay, this is also stator, right? These two are stators. Then deposit and the pattern metal one. The metal one is deposited above stators. Okay, this two metal layer. Know that this metal layer needs to form a good electrical contact with the stators. So you need to form good ohmic contact with the poly 2. In solid state physics or semiconductor physics, you probably have learned that in order to form good electrical contact, we need to have a ohmic contact. Or in other words, poly 2 need to be heavily doped. That's the reason we need to coat a PSG layer above poly 2 to heavily dope this polysilicon layer. Finally, the polysilicon micromotor is released in HF. So oxide layers, the two oxide layers, two PSG layers, are removed by HF. And the rotor now becomes freestanding after sacrificial layer etching. And it is constrained by this cap, right? So it can only rotate, okay? This rotor can only rotate, no translational movement. I know that due to the dimples etched in oxide 1, first oxide layer, we etch dimple in this step. Now we can see the purpose of these dimples. Right, due to these dimples, the contact area between rotor and the substrate is reduced. Right, so this structure, this dimple structure, have to reduce the contact area and reduce the friction. So now we can see that rotor is made from which polysilicon layer? Rotor, poly 1, right? Poly 1 is actually the second polysilicon layer. The cap is made of poly 2, right? It's capped poly 2. And the stators are made of poly 1 and poly 2. Questions? Question? Last slide for tonight's class, polysilicon hinge structure. Know that with a conventional surface machining, the devices or structures are made in the plane parallel to the wafer surface. But that's the nature of surface machining. With the help of polysilicon hinge structure, we can fabricate or assemble out of plane 3D structures. That's the purpose of function of polysilicon hinge structure. This is a 3D view of the hinge structure. We can see it's similar to the hinge used for windows or doors. Right? It's simply the polysilicon hinge structure is simply a miniaturized version of the conventional hinge used for windows and doors. This is the simplified fabrication process. This is cross-sectional views. First, deposit PSG1, the first PSG layer, then deposit and pattern poly 1, then deposit PSG2. Next, pattern PSG1 and PSG2. Okay, we pattern PSG1 and PSG2 at these two locations. Then deposit the second polysilicon layer, right? Poly 2. Right, this poly 2 will serve as the staple of the hinge, right? The staple, which constrains this hinge plate. Right, that's poly 2. And this is the cross-sectional view after sacrificial etching, right, after removing PSG1 and PSG2. And this is a top side view. So you can combine the cross-sectional view and top side view, right, to understand the structure of this polysilicon hinge structure. Right, simply this hinge structure. This yellow pattern, okay, stands for the staple. Okay, this is the yellow pattern. This yellow pattern represents staple. This red pattern represents the polysilicon or this plate. Okay, this is a polysilicon plate. So we can say this plate is made from poly 1. The staple is made of poly 2, right? This yellow layer. And the staple anchors to the substrate. So these two areas, okay, these two areas are patterned in this step. Okay, and then this plate can be rotated out of plane. So we can make some 3D structure, right, based on this hinge structure.